Welcome everyone to the last presentation of today. We're going to bring to you feedback insights and talking about bringing an unsupervised machine learning model into production. I think we have already been introduced. Nikki, would you like to add something? Or shall we get started with the presentation? I think it's nice, and we have a bit more time for questions and answers. So agenda for today, we want to bring 3 stories to you. The first part will be about the business case. So what kind of problem are we trying to solve? The second part, where Nikki will jump in, is about the machine learning part of the project. So which models did we try and how did we evaluate the results, since our model is unsupervised? And last but not least, we will talk a bit about the engineering part. So how did we bring this model into production? So let's start in the very beginning. So how do we collect feedback at ING? And if you're an ING customer in the Netherlands, these screens might look awfully familiar to you. They're from our mobile banking application, and we have small front-end components that on different pages and different section of our applications, where customers can give us feedback. So they can select sort of like an emoji, and then they can also elaborate a bit further on the feedback in form of free text, so they can really describe their problems. And that feedback will end up in, on the other side of the coin, basically in the voice. And the voice is a internal application that is only accessible to us ING colleagues, where mostly our business colleagues can access the customer feedback. So you can select your survey, and then you can see what are the answers to your survey. And as you can see on the right-hand side, we have a really overwhelming amount of customer feedback on these surveys. And especially the open text is really difficult to analyze manually for our business colleagues. So they came to us and they said, hey girls, we have enough data, but we have no insight because it's so much. And we need you guys to help us bring insight into all of this data. And there we come to our solution. Now you can go next. Yeah, perfect. Feedback clouds. So what's a feedback cloud? A feedback cloud is very similar to a word cloud, but in the sense that the bigger the item in the word cloud, the more underlying feedback is in that item. So let's take the word cloud that we see here on the slide. When it's about credit cards, there must be an issue with credit cards at the moment. So now the business users could interact with this feedback cloud, and they could read into what is underneath credit card. Now, the important difference here is that it's a bit more than just a word cloud, because if you look into the other items, you can see that we have a bit more context around the words. So it's very clear that from on the lower end, on the bottom of the word cloud, the item inloggen app is about logging. There's something going on about logging into the app. It doesn't just say app, but the business user or our product owners, they immediately know, okay, there's something about logging into the app. So it's a bit more, it's contextual. And it's important to say that when we came up with this solution, this was a mock. We didn't even start to develop a model yet. We just proposed this to our users and said, would that be something that you like to have? Because our product owner of the team, The Voice, he didn't even know what we were trying to build yet, but it was just about bringing insight into customer feedback. And now we had the challenge, okay, the users really like this. Now we have to build it, and we have to develop a model for this. So, Nikki, can you tell everyone how we did it?
Yeah, of course. So now I will explain more about our journey of creating the model. So to create clusters of similar feedback, as shown in the previous slide, we defined several steps, which you can see here on the screen. I'll explain each of these steps in more detail. So when a feedback response comes first in, we first remove stop words of the English, French, and Dutch languages, as those are the languages that are supported for feedback at the moment. And we also remove punctuation from the feedback text. Next, we create a numerical representation, also called an embedding, from our text data. To create these embeddings, we explored several options. This was one of the most challenging steps in creating our model. So on the next slide, I will explain which models we tried, and then I will explain how we evaluated them before explaining the rest of the pipeline. So now it's time to talk about the different models and algorithms we tried, but due to the time limit, I only will give a high-over explanation. So the first model we tried is one of the most popular models for the creation of numerical representations from text data. It's a two-layer neural network where the vectors of words that are more similar to each other are closer together in the vector space. So in this example, king and queen would be closer to each other than, for example, king and woman. We create a vector for each word in the feedback and take the average of all vectors afterwards to have one vector basically for each feedback response. Then the second model we tried is doc2vec, and as the name suggests, this model depends heavily on the previous model. But instead of creating word vectors for each word separately and taking the average afterwards, we create one representation for the entire feedback response. And this is done by the introduction of a document ID, from which we try to predict the words. And we use this document ID as the representation of our feedback response. Then the third model we tried is BERT. It stands for Bidirectional Encoder Representations from Transformer, and it's a model created by Google. It reaches state-of-the-art performance for many NLP tasks like question answering, so we had really high hopes for this model. I think at some point, Maike and me said to each other, oh, how cool would it be if we can bring a BERT model to production? So yeah, this was kind of our personal favorite. Then the fourth model is a more simple TF-IDF model. We think it is good practice to also include a simple model. So this model basically counts all words present in the feedback and then applies a method called TF-IDF, which gives a lower weight to words that occur often in the feedback. And these can be words like you, I, that, words that are less important, and words that you mostly don't want to cluster on. So now it's time to find out which of these models gave us the best result. But first, I will explain how did we evaluate these embeddings. Because this is not so straightforward as our model is unsupervised. So next to manually looking at results, we also created an evaluation framework. And this framework really helped us in the selection of the embeddings. We based this idea on Sentival, and this is a framework created by Facebook. This framework evaluates embeddings on different downstream tasks. We created tasks specific for our data set and trained a classifier for each of these tasks with the embeddings from each of the models as input. So a little bit more about the different downstream tasks we included. So the first task was predict question. It includes data with answers from two questions. How could ING improve its service? And you're positive about the contact with ING because we created embeddings from these answers and predict whether the feedback is answering to question 1 or to question 2. Then the second task is a semantic match task. we create embeddings for 2 feedback responses and want to predict whether they have the same meaning or not. So in the example, you can see cannot find my yearly overview and cannot request a new scanner. They don't have the same meaning, so the outcome should be 0. While great app and nice mobile application have a similar meaning, so the model should predict a 1. They're the same. Then the third task we included was to predict the topic of the service. So within ING, we ask feedback after different processes. For example, after applying for a mortgage, and we also have service, especially for business customers, or we have a generic service for the app. And we created embeddings from all of these surveys, and then the model needs to predict, okay, this feedback response belongs to a survey about mortgages, this belongs to the generic survey of the app. And for all these tasks, we have an important assumption. So if a model receives the highest score on the downstream task, it generates the best embeddings. So what this basically means is that we believe that if embeddings contain a lot of information, then the classifier on top of it is able to be more accurate in the prediction. So then now it's time to look at the results. So over here in this table, you can see the accuracy of each of the tasks for each of the models on the training and test set. So you can see that BERT had the highest score on the predict question, TF-IDF on the semantic match, and TF-IDF also on the predict survey. So after also a more manual evaluation together with the evaluation framework, we decided to go for TF-IDF. And one of the very important things here was that the results are also easy to explain. Of course, all models make mistakes sometimes, but for TF-IDF, when the model makes a mistake, it was easier for the user to understand why the model would make a mistake. And that made it much less, and that caused much less confusion. So we noticed, especially when we showed the BERT results, and sometimes the model had great outcomes, but sometimes when there was feedback in the same cluster, which had a total different meaning, and this really confused our users. And they kept on asking questions about that one error, so we did not feel comfortable putting that in production. The extra benefit of TF-IDF is that the way we use now is really easy to expand to new languages, but the downside is that it's not based on meaning. So with TF-IDF, because we use a vocabulary of 10,000, we end up with a factor of 10,000 times 1. Then we reduce the dimensions to around 301, because it makes the clustering more efficient. We use truncated SVD for this. And in the next step, we cluster the vectors together using hierarchical clustering. Not every feedback quote needs to be part of a bigger cluster, because for our data set, some feedback responses are describing very unique problems of our customers, so they don't need to be clustered into a bigger cluster because they're just standalone. And in the last step, we create a representation of each cluster. This is the text you saw in the feedback cloud that Maike showed. So for example, rekeningkosten betalen. We use business rules to create the cluster name. And we do that by looking into the words that occur in a cluster, and we show the words that occur most often. We make sure that if there's a plural, for example, account and accounts, that only one of those words is included in the representation. So we use, and there we actually use a small model that compares the similarity of the different words. So now I did a lot of talking, and I think it's time for some real action. Unfortunately, I'm going to show you a notebook as this is a live stream, so I cannot show internal data. But the data you will see over here is from the App Store, so it's public data. Okay, and I've already loaded the data set. It contains 1,072 feedback responses, and I will now run the model. So, for example, you can see that 23% of the feedback is in this table. The biggest cluster is rekening, account, iPad, stands. Then something about the dark mode of the app, something about notification, push notifications, and an update of the app. And next to the table, we can also show the results in the word cloud. And in our final product, our colleagues are able to click on these words in the word cloud, and then they will see the feedback that is underneath this cluster. So we can mimic that a bit here. So for example, when I go to dark mode app, I can see all the feedback that is in this cluster. So here, good app would be nice if there was a dark mode, needs a dark mode. Only downside that there's no dark mode. So I guess the dark mode feature is like a really often requested one. We should think about providing that to our users. And then notifications later push as a second example. Push notifications do not work. I don't get a push notification. Oh, now I get them again. Yeah, so also worth looking into the push notification as apparently they're not working for all customers. Yeah, so this was a demo of our product. So it's now it's time to learn how we put this model into production, and Maike will explain you more about this.
Yes, thank you, Nikki. Really nice demo. I think by now everyone knows what the model is about. So yeah, let me take you guys through how we put this model into production, and I'm gonna do it let's go through the architecture from a user point of view. So on the lower side of the slide, you see our front-end application, and this is the voice, like I already mentioned in the introduction. So if now I am the business user who's curious about customer feedback on my feature, I'll log into the voice, and I click on my survey. And once my survey opens, I will get a word cloud. So where does this word cloud come from? So once I click on a survey, our front end sends a HTTPS request to our backend application, and the backend application is the general backend application of the voice. And then within that request, there is also a bit of information about what type of survey I clicked on, what time frame I selected. Maybe I applied some filters, could be. Now that our backend application has this information from the request, it will send another request to our database, and our database contains all the customer feedback. Now, depending on the settings the user selected, that type of feedback will be extracted from the database. And then after that operation has succeeded, the backend application will send another HTTPS request to our model container. So the actual machine learning model is hosted in a Docker container on our private cloud infrastructure at ING, and it's a Python API. So the backend application is a Java API, but it talks to a Python API. Yeah, and once the model has made its predictions, we'll get the response from the model again through the backend application. And once that response is there, the backend application will also be able to respond to the front end again. And within that response, you have the cluster name, you have what type of items are in the cluster. to be parsed by our front-end component and make it look very nice in a very nice design for our users. So this is how it works. Now, let's keep it real, I would say. We are training a model in production on every request, basically. So we don't have a pre-trained model in a pickled file like you might have it with a supervised model, but we do really cluster all the feedback on every request of the user. So there are a few caveats in this sort of diagram that I showed you. So first of all, there's only so much data that you can query in a batch from your database. So of course, if your database can only handle 5,000 in batch at once, you have to build your API according to that. So there we have a limitation. Same goes for our protocol. So we chose to communicate with our model over HTTPS. Now, also HTTPS has its limits, right? You cannot send 10 gigabytes of data over HTTPS. Let that all be serialized and deserialized in different systems. And then eventually, also train your model, right? So our Python API also takes time to train, and the more data we send, of course, the longer it takes time to cluster all this data. So we had to really coordinate it very well with our timeouts, because if it takes too long, your applications just time out. Yeah, and of course, it's not if we have users that want to make word clouds from a large data set, we cannot serve that in the voice. So then they have to reach out to us or to our product owner, and then they will get sort of like a batch run. So not really in real time. But we noticed that for most use cases, we are good to go, because most of the time our users, they want to have a word cloud about maybe a feature that they brought live, maybe a bug that has occurred last week. So usually not such big time frames with a lot of data. And also this was our MVP one. So we really wanted to make sure that we do step by step. So once we had a good model, we first wanted to bring the value through putting it into production. And now, if it really proves to be something that the business wants, we can still do an MVP2, MVP3, and maybe also we consider our design choices there. But yeah, this is kind of the whole story. I think now we have really nice 10 minutes for questions.